So the first reaction here is the fuel consumption, and for methane, we see that the fuel consumption, it consumes radicals, and we said that makes methane, you know, a slow burning fuel. And then we have the CO oxidation reaction here, the water gas shift reaction, and then we have here reaction number 3 is the chain breaking reaction, radical consumption, and there's the radical, number 4 is the radical producing reaction, and you see here it forms 2 H radicals. And then we said, okay, so there are some more details here on this, but then we said we can break this down to a 3-step mechanism. So the 4-step mechanism is nice because it shows, you know, where radicals are formed, where radicals are consumed. And if we then set the H radical also in steady state, then we get a steady state relation, we get an analytic expression for the H radical, which also might be instructive. So that's what we do here. We eliminate the radicals here with the last reaction. So I add the last reaction to the first one, and then I get this. So you see the, I mean here the hydrogen just then, the radicals go away. And then I add this one to the second last, and I get this, and this one here didn't have any hydrogen, so that just remains. And then we can, from this, also look at the steady state relation for the hydrogen radical. So I write the transport equation. This L here is just an operator that includes the time-dependent term of the concentration or the mass fraction of H. It includes the convection term and the diffusion term. And then all that's left, which is on the right-hand side here. So that's just a short notation of, you know, all the left-hand side of the species transport equation. And then on the right-hand side, we just have the chemical source term. And the chemical source term is here. Hydrogen is consumed here by reaction 1. So this is here, minus omega 1. And then it's consumed by reaction number 3, minus number 3. And then it's produced here by reaction number 4, so plus number 4. You see each one is 2, 2, and 2. So the factor of 2 here, it just goes away. And then this here now, see these rates, they are written here, and I can, plug this in and solve the whole thing for concentration of H. And that's what you get here. And, there's some constant, which is called here H equilibrium, is defined. It doesn't really matter. It's not important. What's important is, the structure, how this looks like. Now, there are 3 interesting facts that follow from this. If this is the analytic solution for H radical, and you see it's a square root of whatever is in these parentheses, and the parentheses have 1 minus these other 2 terms, which means this is only real. It only gives a real solution if, of course, the argument is larger than 1, larger than 0. So if these 2 terms, each one, are smaller than 1, okay? And so if we first look at, so what are the 3 terms? I mean, this here, you could say the 1 that represents here reaction 1, chain branching, that produces radicals. 5 was chain breaking, and 11 is just the initiation, is the fuel consumption. And so if we first look at this last term here, turns out if you are at high temperature, let's say here above 1400 Kelvin, then K11 by K1 gets very large, okay? So that means, for high temperatures, you only get a real solution if this ratio, methane to O2, is very, very small, okay? So that means in the inner layer, the methane needs to be consumed quickly, and then it must be close to 0, at these higher temperatures, okay? So that's number 1 we see here. And then 2, the equation cannot be valid in the preheat region, because in the preheat region, the temperature is below the inner layer temperature. And we know, I mean, that's how we define the inner layer temperature. We know that this ratio then here is larger than 1. I mean, then K5 times M becomes larger than K1. And so that wouldn't work. So, and from that follows, and that's the interesting part here really, that the hydrogen concentration has to vanish in the preheat zone. It must be 0. So that means this shows here that the preheat region must be chemically inert. And it also shows that hydrogen and methane, they cannot exist at the same time. You either have hydrogen or you have methane. If they come together, and that comes here really out of this first reaction, if they come together, then this reaction consumes them both at the same time, okay? So that again, I mean, we looked at this before, or we can look here at simulations. We looked at this before where you see that this blue here is this is a premixed flame. Here the temperature as function of x, the spatial coordinate through the flame. And then you see once we reach this 1000 Kelvin, hydrogen goes up, and below 1000 Kelvin, hydrogen is just 0. And then I should have plotted here also the methane mass fraction. Methane would go to 0 at about the same point. And then on the right-hand side here, you just see that, again, what this here shows, first the fuel is converted to CO, and then the CO is oxidized. That's what's shown here. The fuel here is converted to CO, and then the CO then in this oxidation layer is oxidized. Now, yesterday somebody asked a question. Maybe I didn't make this really clear. Maybe I forgot to mention this. Somebody asked the question. We talk about flame thickness. Is that the preheat region, or is that the reaction zone, or what do we call the flame thickness? And in fact, the flame thickness is all of it in a way. Okay, so that's how we defined it. We just looked at the temperature profile, and we said flame thickness is from, you know, where the temperature starts rising to where it stops rising, kind of. And so it's all of it, but at the same time, it turns out, and that's the point I forgot to mention yesterday, the inner layer, the reaction zone, is much, much thinner than the preheat region. Let's say a factor of 10 thinner than the preheat region. So you might as well say, so the thickness of the reaction zone, it doesn't really matter in the whole thing, okay? So you could say the thickness is kind of given by the preheat region, but of course it's meant to be the whole flame. So we have, here we have really 3 different regions. One is the preheat region, which is chemically inert. Then there's a region where the fuel is consumed. That's what we call the inner layer, where the radicals are formed, where the CO is formed. And then there is an oxidation region after that, where the CO is oxidized to CO2. And as you see here, this can also be quite broad. Okay, so then if we look at, you know, how does the structure of a flame look like when we consider multi-step chemistry, even this 3-step mechanism is a little difficult to consider when it comes to mathematical analysis. And so here this analysis starts out by first reducing this even further to a 2-step mechanism, where H2 and CO, they're both stable intermediates where they're kind of put together. Okay, so there's a factor alpha here which gives the ratio of the 2, but you see these always appear now together. And so that's a further assumption is being made. And now for the analysis, what does it mean if I have 1-step, 2-step, 3-step, or 4-step? For the analysis, it really means each individual step has its own time scale, okay? And so this means that, I mean, if I'm a fluid parcel now, or fuel molecule that flies through the flame and is being converted maybe to CO, and all these things happen, then there is a delta x, a length that corresponds to the time scale of that reaction divided by the burning velocity, right? That's the, or by the local velocity, you could say, which is the burning velocity. That's kind of the length. And if you have a fast reaction, that length is really small. That gives you a very thin layer. And if you have a slow reaction, that gives you a very broad layer, okay? So each reaction happens in a certain layer. That's why we always talk about these layers. And so if I have a two-step mechanism, I should get two layers, kind of. So here, the first one, again, is the conversion of methane to these stable intermediates. That's one layer, that's the reaction zone here. The inner layer, that says here is order of delta, and this here, the preheat region is order 1, is defined as order 1, and then this here is order delta, and then I have this reaction which converts now the stable intermediates into products, and that's the oxidation layer that is, you know, wider than the inner layer. And if I compare the three, then this one here is order 1. The oxidation layer is much, much smaller than 1, and the inner layer is much, much smaller than the oxidation layer. Okay, so that's kind of how they are arranged. Okay, so here's a lot of information about the analysis, which we're not going to follow through, but you have the material. You can do this if you want. See, it goes on for quite a bit, and then we just look at the result. So this is the result now, which comes out of this analysis, and you see that now, you know, it's a lot more complicated than what we got from the thermal flame theory, and in fact, here you have all these different reactions that are appearing. What's interesting is that, first of all, is that the result here, it does not only depend on the burnt temperature, on the adiabatic temperature. We said earlier in the thermal flame theory, we said that's it seems to be very important. A high burnt adiabatic flame temperature, it makes this thing really fast. And you see the same thing here also. It depends on the burnt temperature, but then at the same time, it also appears on the inner layer temperature. T0 also appears here, and the T0 itself comes here from this relation, which is also an implicit relation here for T0. And so graphically, this is shown here. This here gives a relation between T0 and pressure. So if you fix the pressure, if you say, I want to know what's the burning velocity at 1 bar, so you fix the pressure, and then you have an implicit equation here, but I can also plot, you know, from this equation, I can plot the pressure as function of the temperature. So I can specify T0, you know, plug it in. These are all exponential functions here. Plug it in here and then get the pressure, right? I mean, that's much easier. And I can draw the line like this, and then I can go the other way. You know, 1 bar then corresponds to this point on the line, which gives me an inner layer temperature of maybe here 1300. And then I can plug this in here, inner layer temperature of 1300. This here is SL as function of inner layer temperature, and then it gives you a temperature here, flame speed of 54 centimeters per second, which is not what we said, what we saw from the experiments. From the experiments, maybe it was more like, you know, a little less than 40 centimeters per second. But you see, it's not totally wrong, right? I mean, that's the analysis. Okay, so no tuning here, just approximations. And then this is what you get. The other thing that's interesting is that you see the Lewis numbers appearing here. I mean, the transport is a part of this. And then maybe the other thing that's interesting is that only reactions 1, 5, and 11, chain breaking, chain branching, and the initiation are part of this. The CO oxidation reaction, it doesn't appear here anymore in this. And that's immediately, let's say, that's a drawback here. The reaction 9, it doesn't appear. Or does anyone see reaction 9? No, I think it's not here anymore, and that's a drawback. I mean, we know if you do sensitivity analysis, you see that the reaction, that the burning velocity is actually very sensitive to the rate of this reaction here. So, I mean, that's, you know, that's an approximation. But anyways, okay. And then here's another interesting consequence of this relation. That's really interesting. It says that if I dilute now, let's say, so look at this here again. This is the relation for the inner layer temperature for T0, right? And that depends only on the pressure. There's nothing else that affects this, right? If I fix the pressure, it gives me T naught, okay? Now, it does not depend on the composition, for example. Now, the adiabatic flame temperature depends on the composition. A small equivalence ratio gives me a small adiabatic temperature, right? Or very high equivalence ratio, same thing. So, this means that if I dilute the mixture enough so that TB gets smaller, 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 if TB is the same as the inner layer temperature, then the burning velocity will be 0, okay? So that means the flame doesn't burn anymore, the flame will extinguish. So that's that's interesting because we said for the thermal flame theory, you make the temperature lower, 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 you know, it gets slower, 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 but it will never go to 0. The burning velocity will never go to 0. But here you see there's a kinetically controlled lower limit, you know, of the, let's say, the equivalence ratio or dilution or whatever of the maximum temperature, a kinetically controlled limit. If you go below this limit, then the flame will extinguish. Okay, so that gives you a hint for the flammability limit, for example. So that's what we will use later on. I mean, and you see here, for example, here, if you, this is reached at 1 bar at about 2320 here, and yeah. So we'll look at this later on. This, you know, there's, I mean, for the thermal flame theory, we looked at the time scale that results from this. You can do something similar here. There's some more discussion on what is the difference and what's the same as in the thermal flame theory, but again, we're not going to discuss this now. Now, one other interesting aspect that one can do with an analytic solution like this, the analytic solution might not be 100% accurate, but it gives you the dependence on different parameters, on different, you know, on the temperature. For example, would you have guessed that the temperature here that, you know, is TB minus T0 to the 4th power, and, you know, there's another TU here squared in front of it and so on. Probably one wouldn't have guessed this. So what we can also do with this, we can use it as a basis function for deriving a fit for the burning velocity, okay? So that's something people have done. So take this, but not exactly this, you know, just take here the general dependence. You see you have TB minus T naught divided by TB minus TU here. This is to the 4th power, just put an N here, and then this here looks similar, and then, this actually 2nd power if I take the square root of this because there's SL squared here. So this is a 2, and then, you know, this is the same as here, and then all of this here, you know, it's just a function of T naught, and so on. And so this is, you know, there's a lot of exponentials here, so let's assume this is an exponential function. And T naught also is given like this, and then E and B here, they are just also fitting parameters. So we use this, and then we develop for different fuels, we determine these parameters here, N, M, and G, E, and B. We determine these from a fit. And so this here shows this for different fuel, for many different fuels actually, you know, shows these parameters. And you see here we said, for example, N, you know, from the asymptotics it came out to be 2. And you see here, it's not totally wrong. Usually it's a little larger than 2, but you know, is something of that order. And then here these other parameters like this G function, sometimes positive, sometimes negative, it can have different values. And then TB also, you know, is a quantity that appears that's just fitted here with the equivalence ratio. All of this is valid only for lean up to stoichiometric mixtures. And then this is what you get. Here's for methane, SL as functional equivalence ratio for different pressures. And here the circles, they're always from simulation using detailed kinetics. And then the lines are the fit, and you see the fit is not so bad. And then this here is the same for propane, also not so bad, or similar for propane. This is here for function of pressure for different temperatures. and so on. So that's just a fit, and then here this shows how one can use the fit to determine here to answer some questions. It's just an exercise or an example. Now this is another way how we can fit burning velocities, of course. I mean, today if we want to fit something, we use machine learning type models or artificial neural networks. So this shows an example here where we have used an artificial neural network to make a fit for methane burning velocities, and then of course you can do this for lean. Most of these fits, they work only for lean flames. This works then of course for all equivalence ratios. It's compared here with the asymptotic model, and there's also something here, the Gülder model. People use these models in simulations, for example, for internal combustion engines. You have an internal combustion engine, you use a flame speed based model, then you need the flame speed, the burning velocity as function of pressure, temperature, and so on to plug it in for example, the level set equation. So people use these functions, but there is an issue because sometimes they're not all that accurate. And so here we have used a chemical mechanism to generate data then that we use here for methane air. This is for natural gas engines, and then we train a neural network here with I mean here just some data on the network. It's a very simple network, in fact. And then here we train this up to 120 bar, different temperatures, equivalence ratio from lean to rich, and so on. We use about 80% for training, 20% for testing. And then this is what you get. I mean, you see here, a little hard to read. This is, these are different pressures. All 6 are different pressures. And you see burning velocity as function of equivalence ratio. And the data here is from the detailed simulations, the circles, and then here this black line over this is the ANN model, and this here is the Gülder model, and this here is the fit that I showed you earlier. And you see, I mean, there are two reasons for difference here. Number one, they fitted their data to some other mechanism, to other experimental data. So if there's an offset, that's just because this is a newer mechanism. But you see also that the dependence here can be wrong with these older models. Where of course an ANN it really nails this almost. I mean, except for the few places here where it's not perfect, but it's not so bad either. Here another one that's really interesting. It's a study we did some time ago that supports us in designing new fuels. I mentioned earlier burning velocity is really good for efficiency. High burning velocity is good for efficiency in internal combustion engines. So we want to design fuels that have particularly high burning velocity. But how do we know? How the fuel should look like for high burning velocity. So we developed an ANN-based model that predicts the burning velocity based on the fuel structure. Okay? So you draw for me here a fuel molecule like this, or some more complex fuel molecule, and we just take the structure of your drawing, and I predict the burning velocity from this. Okay? So that's what this network does. So again, it was trained now with a lot of different data for different fuels, first of all. And if you ever need a database for burning velocities, this paper also has the database that we used for this. And then also we did, where we had gaps in data, we actually did simulations using validated models. And this is what you get. This predicted burning velocity versus measured burning velocity is not perfect. You see, I mean, it's not perfect at all, but it's not so bad either, let's say. And now we can predict burning velocities for many, many different fuels. And you see here, here's burning velocity for different fuels. And they're sorted here by the value of the burning velocity. You see an octane that, that's representative of a gasoline fuel. That's actually really bad in burning velocity. And if you look at newer, or here, for example, RON 95, you see that is very similar to octane, but it's also not very good. If you go here to, for example, ethanol and methanol, we know these are really, really good fuels, and they have really high burning velocity. I mean, you see here, they also have good octane number. By the way, we have the same model here also for octane numbers. And so you see these are pretty good. But now we're looking at some newer fuels here. This is dioxolane and dioxane, and these are really, really high in their burning velocity here compared to, for example, RON 95. And then you can also do sensitivity analysis. That's the interesting part. Okay, now the input for the network is the fuel structure. So I can say, take the fuel structure, but take the alcohol group away. You know, how does the burning velocity change? Or I can say, take the fuel structure, take a carbon away, make the chain longer, shorter. So I can do all of these sensitivity analysis and see how different functional groups, you know, how change the burning velocity. So that has been really useful in that. Okay, so that was the burning velocity. I mentioned flammability limits. Flammability limits are very, very important for safety. You know, I mentioned this already. And you see here flammability limits. Limit means in terms of equivalence ratio. Flammability limits for methane and hydrogen as function of the temperature. Okay, so I have a methane air mixture at a certain temperature, and I make the mixture leaner until it doesn't ignite anymore. Okay, so that's what I call the flammability limit. And now, how is the flammability limit determined? It's a little bit an artificial quantity because there's an apparatus, there's a standardized apparatus where I have you know, the mixture inside, and then I have a spark or something, and I ignite it, and then either it burns or it doesn't burn. Either the flame kernel that I just ignited, it goes out, or it burns through the whole thing. And that, of course, depends on the power, you know, of the spark and so on. So it's a little bit an arbitrary definition. But what you see here, and this is here 1 over equivalence ratio. So this here is rich, and this here is lean. And so this here is methane, and you see at higher temperatures. So this is the lean flammability limit, and this is the rich flammability limit, okay? So you see at higher temperatures, these limits get wider and so on. I mean, it doesn't depend so much here on the temperature. But what's more interesting is the blue lines are hydrogen, and you see here so this here is lean, and so especially the lean flammability limit for hydrogen is so much wider. It burns it ignites or it burns at so much leaner conditions than methane. Here you see it's almost a factor of 2, or it is actually a factor of 2. You know, the flammability limit. So that is really, I mean, that shows why hydrogen is so dangerous. You need only very little hydrogen in air to make it flammable. And then the question is, can we predict this? We said earlier, somehow the result from the asymptotic analysis, it looked like this, and we said, I mean, one limit should be reached when the burn temperature reaches the inner layer temperature, okay? So that's what we use. That's a kinetically determined flammability limit, and that's what we want to use to estimate what the flammability limit is. And so we start out here, this is the function, and we say, okay, so TB should be equal to T naught. So we know what T naught is for a given pressure, you know, we can determine T naught. And then we want to know what is the equivalence ratio where the mixture reaches that value of burn temperature, okay? So for that, then we use the coupling function. So the coupling function, again, gives us here a relation between the mass fraction of fuel and the unburned and the temperature. And now we set the temperature equal to the value of the inner layer temperature. Okay, so that here should be the burnt gas temperature. We say that should be that is the condition that's equal to the inner layer temperature, and so from this we can compute this. And now, I mean, to make this a little easier, you know, get rid of all of this, I write the exact same coupling function here for stoichiometric conditions. Then that is then, I mean, y fuel unburned at stoichiometric conditions is equal to TB at stoichiometric conditions, and the rest the same. And then I divide them by each other, so I get Y fuel at the lean flammability limit divided by the stoichiometric condition, and that's equal to T0 minus TU divided by T stoichiometric minus TU. Okay, and then here all of these constants here go away, and so I know what for 1 bar I can determine T naught. You plug this in here. T unburned, I just assume now 300 Kelvin 1 bar, and then I can also T stoichiometric for methane. We said is 2,222 is what I said. 0.22 is easy to remember. I plug this in here also, and then I get here this. And this corresponds now to the equivalence ratio of roughly 0.5. Okay? So we can check this. This here shows the mole fraction of fuel in the unburned as function of T unburned at the flammability limit. These are experiments, and then you see here these are simulations that these are simulations that give this all 10 centimeter per second, okay, and then this here is 5 centimeter per second, and this 2.5 centimeter per second. So you see, flames experimentally they extinguish or they don't burn anymore when the burning velocity, the computed burning velocity, is roughly 5 centimeter per second. So this here should be 0 centimeter per second, and also, you know, it's let's say a simple approximation, and the simple approximation is, you know, a little too low, but at the same time it predicts this trend, let's say, okay, and also it's a lower limit. I mean, this here is 0, and this is not quite 0. So, but it shows that there is a lower limit. Now, what else affects this? Of course, when the flame becomes slower, maybe also, you know, stability, inhomogeneity is an issue. I mentioned the stretch effects. You know, when you ignite this, you have a very high curvature in the beginning. For methane, that would actually make it burn more slowly. That would also bring it closer to this line if that would be considered. And then also radiation plays a role, especially when flames go towards the limit. They burn very slowly, and then radiation becomes important because radiation also is a slow process, but if the flames burn slowly, then also other slow processes become important. Okay, so again here, just, you know, to drive this point home again, the thermal flame theory has no flammability limit. It burns all the way to, you know, let's say unburned temperature. It's just that this exponential term will then make it exponentially slow, but it will never be 0. And multi-step kinetics then very clearly gives you a kinetically determined lower flammability limit. Okay, so that's the end of this section. Any questions? No question. Then we'll go on to non-premixed flames. Okay, so we talked a bit about premixed flames. Now we'll talk about non-premixed flames. And non-premixed flames, you know, there's not so much to say about. I remember I said to my advisor once, why do you, you know, in your book or whatever, I can't remember exactly what it was, I said, you have, you know, so much on premixed combustion and so little on non-premixed combustion. He said, well, non-premixed combustion is simple, it's very easy, okay? Premixed combustion is a lot more difficult. And so let's talk about non-premixed combustion and then also try to see why is it so easy? Why is premixed combustion in a way a lot harder? So I'll give you a short introduction, then we talk about here these counterflow flames, and then we'll talk about flame structure a bit, and then there's a whole bunch of stuff here on single droplet combustion. You have an evaporating spherical droplet, you know, how this burns, and but we're not going to talk about this, but you have the material if that is something you're interested in. So this shows you here different example for non-premixed combustion technical systems. This is here my little burner photo I took a long time ago. This is one example. I mean, you have the liquid, you have a gaseous fuel coming out of the nozzle, you have the air that is in the surroundings, they mix, and while they mix, they burn. There's always a region that's very rich, there's always a region that's very lean. In between, you must have kind of a surface that is exactly stoichiometric, and that's where reactions happen, because that's where fuel and oxygen are consumed, and then on one side you have no fuel anymore, so it doesn't burn. On the other side you have no oxidizer anymore, so it doesn't burn there either. Okay, so that's why for premixed, non-premixed flames, you get the reactions are typically constrained to a very thin layer. This is an experiment that we run in our lab. Is a high-pressure diesel spray injection chamber. Is a chamber that goes up to maybe 100 bar and 1,000 Kelvin. And so there's a slow flow through this chamber. There's a diesel injector, and then you inject the diesel fuel. And you see this here. This is a little slow. I don't know why, but you inject the diesel fuel, and then it starts evaporating. You first see the liquid come in, starts evaporating, and then at some point it should ignite. And yeah, now it ignites, and then you see here how it burns. You kind of see where the flame is and what the flame is. We can use this also to measure, get an estimate for soot and so on. And this is a simulation. Here is a large eddy simulation of a very similar thing. This is here the so-called ECN spray A case. Is a standard test case that people use for testing their models. It's an experiment that was run at Sandia by Lyle Pickett. And you see here also, you see the liquid fuel come in. There's the dark blue stuff, and then it evaporates. There's the light blue stuff. And then at some point you get ignition here around stoichiometric, and then it burns, forms soot, and so on. And so there are different cases, you know, technically where you use non-premixed combustion. We said premixed combustion is good for avoiding emissions. That's, you know, that's usually what we want to do. But in a diesel engine, we use non-premixed combustion. Why? Because diesel engines have the nice feature. And you might know this, of course, but if you take a spark ignition engine, it has a certain efficiency that depends on the compression ratio, and it's a constant volume process. And the diesel engine is modeled with a different process. Thermodynamically, it's constant volume and then constant pressure. It's a combination of both. Why constant pressure? Because we say you inject, okay, and then it mixes a little bit. And after it ignites, there's a lot of partially premixed stuff. And that burns premixed all at once. That's the constant volume part. But then after that, you know, you still have these rich regions, lean regions, and combustion only happens because of mixing. And this mixing process is kind of slow, which is why, you know, it's slow. So we say, you know, it's a constant pressure, not because it's really a constant pressure, but that makes it easy in the thermodynamic analysis, you know, constant pressure process. So, but for the same compression ratio, the diesel process has a lower efficiency than the constant volume process, right? But the nice thing is, the spark ignition engine, you know, the fuel and air are premixed. You can compress it only up to a certain point. In a diesel engine, you compress only the air, okay? And then you can go to much higher compression ratio, and then you inject the fuel. So that's why diesel engines are non-premixed, because you want to compress only the air. So, you know, by compressing air, you cannot get knock. And then you inject the liquid fuel, and there also you can get auto-ignition, because everything that is mixed burns at the same time. So, right, so that's a diesel engine. Jet engine, we use non-premixed combustion typically for safety reasons. I showed you the non-premixed flames are much more stable than premixed flames, so that makes it a desirable feature for jet engines. And then, right, candle flame. I mean, that's the best example. That's the problem here of us combustion scientists. We can have a nice candlelight dinner. I mean, other people can have a nice romantic candlelight dinner, maybe with your partner. And you know, but when I have a nice candlelight dinner, I look at this flame and I think, oh, it's work again. And so what happens here with this candle flame, you have the flame is burning. Here's actually shown in this slide. The flame is burning. You see the yellow stuff we said, that's soot. And that soot glows. And that's what why you get the yellow color. So it's basically black body radiation at a certain temperature. And then the radiation actually quite strong. So that radiation, it heats up the paraffin, the wax here. It melts, and then it goes by capillary forces. It goes in the wick, and then it evaporates from there and creates a rich region here and burns then as a non-premixed flame. If you get too much fuel, you notice that it starts smoking on top. But typically, if you do it right, all the soot is burned out before it can come out in the atmosphere. Or if it ever smokes, just take the wick and bend it to the side so that then you don't get as much fuel. Then it doesn't smoke anymore, or just cut it off a little bit. That's what you learned in your combustion class. You learned something in your combustion class. This premixed combustion on the left, non-premixed combustion on the right is just a review again. I mean, a reminder of. So here, if I go through the flame, I have fuel and oxidizer on one side, the temperature is low, and then if I go through the flame, fuel and oxidizer go away. Reaction zone here happens at some inner layer temperature, and then it converts the temperature in the adiabatic temperature. You know, this heats up, then the unburned gases and so on. But for the non-premixed flame, you have the fuel on one side here on the inside, and the oxidizer is 0, and then on the other side, here on the outside, you have air or the oxidizer, but the fuel is 0. And they diffuse both into this reaction zone. The reason why they diffuse there is because the reactions consume. So the reactions, if they're fast, they make fuel and oxygen both go to 0 in the reaction zone at stoichiometric. And then you keep up this gradient, and you know, they diffuse into the reactants diffuse into the reaction zone. And then the product, you form a product here, and that product and also the temperature, they diffuse out into the unburned gases. That's why it's called a diffusion flame also. It depends on these diffusion processes. So I mentioned soot here, and again, here you see very close to the burner, you see this blue layer on the outside. That's the reaction zone, and then you see how soot is not formed here. It takes actually quite some time until soot forms, because soot formation is also a really slow process. And then you see, on the other hand, oxidation here seems to be a very fast process, because you see, you know, a lot of soot and no soot is, you know, right next to each other. So you have this flame, everything oxidizes away. But if the flame gets too long, heat losses become too large. I mentioned this also already. Then you have the flame can extinguish by heat losses due to radiation, and then the smoke actually comes out on top. Time scales. What's interesting is that mixing. You know, I mean, I said talked about the gradients. The higher the gradients, the faster the diffusion velocity into the flame is, right? Which means the more fuel per unit time will come into the flame. So high gradients make diffusion flames really fast, okay? So is mixing. High gradients make mixing fast. But fast mixing makes gradients low, right? I mean, if you have you know, a lot of stuff here, nothing here, as soon as it mixes, you can have a super large gradient in between. But you know, if you wait 5 minutes, then the gradient, it mixes and the gradient becomes really small. Mixing makes gradients small, okay? So you know, the high gradient actually leads to the fact that you mix very fast, which means you make the gradient small very fast. So diffusion flames, very often they are controlled by this mixing process, because, you know, mixing is very often not as high as we want it to be. And so this means that chemical reactions are often fast, compared to mixing. And so they are mixing controlled. We often use this assumption mixed is burnt, okay, which you know, I mean, really means the reaction rate is the same as the mixing rate of fuel and air, which, you know, sometimes it also works quite well, but it does not work for pollutants. I said this a few times. For example, soot formation is a really slow process. These reactions are not very fast. NOx formation is a really slow process, also not very fast. And so the other thing is we introduced already, I mean, this is all here just a review again of what we discussed already. We introduced the mixture fraction. The mixture fraction tells us locally where the rich regions and the lean regions. We said mixture fraction 1 is pure fuel, mixture fraction 0 is pure oxidizer, and in between, you know, we just see if it's lean and rich, and then here in this equation, if fuel and oxygen are 0, you reach, or they are both 0 at stoichiometric conditions, which means the stoichiometric mixed fraction is given like this, and that's typically where the reactions happen around the surface of stoichiometric mixture. And then we said there's a relation between equivalence ratio and mixture fraction like this, and which means, again, mixture fraction is nothing else than the local stoichiometry, local equivalence ratio. Okay, so when we talked about premixed flames, we started out saying, let's look at a flat, you know, undisturbed premixed flame. That's kind of the simplest thing we could imagine. And now also for non-premixed flame, we start out looking at the simplest possible non-premixed flame we can imagine. And for the premixed flame, this was just maybe an infinitely large burner, you know, with an infinitely large flat flame on top of it, which is far enough away from the burner so it's not disturbed. By the burner has no heat losses to the burner. That was the easiest thing we could imagine. We said that's 1D. And now for non-premixed flames, that doesn't work because you need two streams. You know, you need the oxygen and you need the fuel stream. So the easiest experiment here people have come up with is the so-called counterflow burner. So the counterflow burner has a nozzle here on top. You see oxidizer nozzle here on top, has the fuel nozzle here, let's say on the bottom, and then you blow fuel and you blow air, and then or oxidizer, and then you form a stagnation plane, and then you have on one side of the stagnation plane you have, or maybe in a stagnation plane, but typically we said stoichiometric mixture fraction is 0.05 and pure air is 0, so it's very close to the pure air usually. And so this typically sits on the lean side of the stagnation plane. You have a flat flame, and this is shown here. This is a photograph, a little bit, you know, artistically illustrated here, but you see the upper nozzle here, a little bit dark, and you see the lower nozzle here. And then here you see these two regions, here the reaction zone in blue, and then here a soot layer in orange, and then here really this is then the stagnation plane is where the soot layer ends. So I have here the flame, and then if I go towards the stagnation plane, I go to richer mixtures because this is where the fuel is, and then you form soot, but the soot particles actually don't diffuse, so they just go to the stagnation plane, and they cannot go on the other side of the stagnation plane. Okay, so that's why you typically, you know, you get a sharp, kind of a sharp interface at this, or, you know, for soot at the stagnation plane. And this is how this then looks like. One of the things that will be really important in the analysis is to have a top head profile. So the top head profile, so we use here contoured nozzles that are designed to give you a top head profile. Turns out though, if you have one of these contoured nozzles, it gives you a perfect top head profile because that's how it's designed. But when you put two, you know, they blow against each other. It's not top head anymore because you create a higher pressure on the center line, and then you kind of get a velocity dip, you know, on the center line. And So people use, you know, meshes and or porous plugs here to get this top hat profile. But the top hat profile is really important. Just keep that in mind. So if you ever run a burner like this, make sure you have a top hat profile if you want to use this for computation. Now, what's interesting about this is also that you have a time scale now, because you have velocities from both sides, and you create a strain. Strain is a velocity gradient, right? And so if you blow harder, higher velocities, the gradient gets larger, and you know, with that also all the gradients of the velocity of the species profiles and so on. So that's measured then by the strain rate, so-called strain rate, and the strain rate is a velocity gradient, so it has units inverse of a time, seconds to the -1. So we can use it to define a flow time scale. So the strain rate, 1 over the strain rate is a flow time scale. Okay, is how long is a fluid particle in the flow. Okay, so and then we have a chemical time scale. So these two together, they give you a Dampköhler number. And in this experiment, that's a nice thing. You can change now the Dampköhler number. You can blow harder, harder, harder until and harder means that the flow time scale gets smaller. And if it gets small enough, then the flow time scale and the chemical time scale are of the same order, and then something interesting must be happening, right? I mean, if the flow time scale gets shorter than the chemical time scale, then it really means the chemistry can't happen anymore, and you blow the flame out, okay? So that's, by the way, it's the same thing. I come back to the romantic candlelight dinner. If you blow the flame out, all you did was you increase the strain, basically, and you decrease the resonance time scale, you decrease the Dampköhler number, and then the flame goes out. Okay, so I don't know, yeah, so this is this region here. And now we can write down the equations that, now here's the problem. This McKenna burner, premixed burner, that was 1D just by itself, right? This here is not 1D. I mean, you see, you have a stagnation region here, a stagnation plane, and the velocity, I mean, the streamlines, they go, you know, outside like this. This is not 1D, okay? So this is 2D. If it's rotationally symmetric, it's still 2D, okay? So that's a problem, because 2D simulations with deep chemistry, they're very, very expensive. And so 1D is better. So we start out with the governing equations. You have continuity equation. The x coordinate here, you see, is 1 over x d by dx of rho x u. That's the equation in cylindrical coordinate system. So the x coordinate here is the radial one, and the y coordinate goes from nozzle to nozzle. In a way, it's a little counterintuitive for some of you, but of course, you know, all of this comes from the people doing fluid mechanics. People do fluid mechanics. They use, for them, y is always the coordinate in direction of the boundary layer, you know, if you think of boundary layers. And so all of this comes from fluid mechanicians, and the similarity solution actually is, so this is kind of a boundary layer, okay, in this direction. That's why we use y in this direction and x here in the radial direction, okay. So then we have the momentum equation. Turns out the second momentum equation you don't need is the pressure, and then here the velocities. These are all just viscous terms, you know. I mean, the exact form of this is not so important. And then you have the energy equation here written in terms of the velocity, in terms of the temperature. You have Cp here. You know, this is the heat conduction term or thermal diffusion, chemical source term. And then here these are other transport terms also, which are not all that important. I mean, yeah. So then we want to develop a similarity solution, and that's the trick here. Now we introduce a similarity coordinate in a way that we reduce this 2D field into a one-dimensional solution. And so we do this by first saying first assumption is that u velocity is proportional to x, and it's only a function of, otherwise it's only a function of y. That's a similarity assumption. And then the second similarity assumption is we assume the pressure can be written in terms of x and y separately, okay? So the x dependence and the y dependence, they're additive and multiplicative. And then also here we assume that the pressure here goes with x squared. That makes sense here in terms of the velocity, and that's also a similarity assumption. So basically what you do here is you make assumptions. Let's say from experiment, you know it has a similarity solution. And then you just make assumptions such that it all reduces into one dimension. So these are these assumptions. If you plug this in, you will see this is what you get. And all of a sudden, the x coordinate here disappeared, okay? So this is all a function only now of y. And then you have this g. G is a function here. G is a function of y. It's not a function of x anymore. But you could reconstruct. And then, sorry, the third one I forgot. And then we also assume that mass fraction and temperature have no radial dependence close to the center line, which really means here in this direction, it should it should be all the same. And you see here that's kind of, I mean, if the nozzles are designed right, these flames are really nice and flat. And at least the third one here is well justified. And then, so this is the system of equations. Now we can write, have boundary conditions here. You have upper velocity, lower velocity, temperatures, and mass fractions. And then these can be solved in 1D. I mean, that's a nice thing. Now we have a one-dimensional similarity solution, and we can solve this flow field in 1D. So that's shown here then. For example, this is from measurements here we did using time-of-flight mass spectrometer in this device. And you have here different species. This here is the fuel, is an acetylene flame. So this is the fuel nozzle. And then here you have oxygen. So here's the air nozzle. And then you have a lot of other species here in between, and a comparison with some chemical kinetic model. And of course, I mean, these here are not all that interesting. What's really interesting is now look at larger aromatics, pHs, and things like that, which was the purpose of this study. Okay, so from this, I mean, here this shows similarity solution. What we have done here is we assume from the beginning on, we assume that you have two nozzles and that the whole flow field just goes from one nozzle to the other. You could also assume, that's for the analysis sometimes interesting, you could also assume the flow really comes from infinity. The flow comes from infinity, and then it's a potential flow very far away from the center line, and then, at some point it starts turning around. And so that's what's often used, is this, and then you also get a similarity solution. So that similarity solution is shown here, where eta is here a coordinate in this y direction and so on. So we don't need to follow through this, but that also leads then to analytic solutions. So this here shows then numerical solutions of these equations that I showed you, and what you see is the temperature, for 3 different strain rates. And I mentioned earlier, if you blow harder in both nozzles, then the strain rate is high, and then the gradients become larger. The whole flame becomes thinner, and that's what you see here. The lowest strain rate here gives you a very wide temperature profile. I mean, this upper one here actually goes like this. I mean, it's not shown all the way, right? I mean, but it goes all the way to this point, and on this side here, all the way to this point. And then you have here obviously, the colors are switched. You see this? This here is obviously the highest strain rate. The red and the green is the second highest strain rate. So the green really is the 1 per second, and this is 500. So this here is very, very close to extinction. This is a little higher, and you see the profile, it gets narrower. And then when you blow even harder, that's what I said earlier, then the local residence time, the time the flow is in the flame, becomes of the same order as the chemical time scale, and if you blow yet a little harder, flame extinguishes. So this here is very close to extinction. That's why, you know, the values look kind of funny. This is very close to extinction. If I would blow just a little harder, this would extinguish, okay? So, but you see, you know, it's a wide range. Now, if I plot this as function of mixture fraction, then, of course, they're all normalized between 0 and 1, and you can actually compare them a lot better than here in this case. And you see from 0.01 to 1, not much happened here, really. But then here, this one's close to extinction. It looks very different. So why is the temperature much lower? Why is the temperature much lower? Because, I said earlier, you have fuel and air comes in, and it burns. It increases the temperature, and so you release thermal energy, and then the energy diffuses away. Okay? So that gives you then a certain temperature, which if the chemistry is infinitely fast, then fuel and air are all consumed, you know, right here at the maximum temperature point, and the temperature is highest at that point, and it should actually reach the adiabatic temperature, roughly, right? But what happens if I increase the strain? Then the reactions, they have less time to complete. And now you have fuel and air come in, but it cannot be fully converted. You know, it's only, let's say, 90% are converted. So then also the temperature is only 90% of what it's supposed to be. And if you make the strain rate even higher, even less gets converted, and so on. And that's why at some point the temperature gets lower, 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 and then at some point it will extinguish. So I can actually do simulations for for all possible strain rates, let's say, and then I just plot the maximum temperature as function of strain rate. And that's shown here. This is the maximum temperature as function of strain rate, and you see, you know, this is 0.01, and here's 1, and then here's the 500 whatever, and that's where it actually extinguishes. So, right. So these counterflow diffusion flames, they're good for two things. Number one, it gives you a way to measure chemical time scale. Okay? So you have a fuel and a certain mixture, certain thermodynamic conditions, and you're wondering what is the chemical time scale. You actually increase the strain rate until it extinguishes, and then you can say, this is roughly the chemical time scale, is, you know, 1 over the strain rate. That's number one. That's interesting. That's just like the burning velocity is a good calibration parameter for chemical models, or validation data for chemical models, whatever you want to call it. And then second, what I really like about diffusion flames, I'm a big fan of these counterflow burners. Actually, you could also run these premixed, right? I mean, you could have a fuel-air mixture on one side and a fuel-air mixture on the other side, and then you get a twin flame, you get two flames, and it's fully premixed. But now, in contrast to the burners we discussed earlier, now you can also control again a chemical time scale. You know, you can control fluid mechanical time scale. You can blow harder, and at some point also these premixed flames, they will extinguish. So, you know, I think I'm a big fan of these. Why? Because first of all, you can change the Damköhler number. That's very important. But second, one of the big aspects we mentioned earlier about these McKenna burners, I said they're always very close to the nozzle. They interact with the nozzle, and you don't know how they interact with the nozzle. You don't know what the heat flux is into the nozzle and all of this. Here for these, so that's why when we do simulations of these premixed flames, burner stabilized premixed flames, we use a trick. Anyone knows what the trick is? The temperature profile is actually, it's typically measured. So we do the simulation prescribing the temperature profile. We don't compute the energy equation. We don't solve the energy equation. We get the temperature from the experiment, okay? Because you cannot predict it, because you don't know what the heat flux is in the burner and so on. Here for these counterflow burners, the flame is away from the burner, right? It doesn't sit on this burner, it doesn't sit on the other burner, somewhere in between. There's no problem predicting the temperature, okay? So, you know, there's no interaction with the burner, so it's much better behaved also in terms of being able to do experiments. Okay, so then if we look at the flame structure, we could also follow through in a similar way as we said earlier. We could, you know, look at thermal theory and so on, and I'll talk about this briefly later on, but we're not going to go to the details of this. Instead, we said earlier, sometimes the reactions are really, really fast, and we can assume mixed is burnt. But that's not always the case. That's not the case here. For example, any time, chemical timescale is important here, for example, for lifted flames, for local extinction, for pollutants and so on. Are we out of time again? Are we late again? Okay, why don't we just stop here? Hey, this shows that you guys are really mature and grown up. Because when I teach an undergraduate course, and you're 2 seconds over the time, nobody says anything. You just hear people with a pencil, you know, they just get very noisy, and you guys are very well behaved at that point, but you can actually remind me. Okay, so let's meet at 3:25.